In this paper, we present a model-based learning solution to the object retrieval problem. Object retrieval can be hard. Especially retrieving an object from densely packed objects, there is no free space for inserting a gripper around them. One or a sequence of push actions is needed to help to create sufficient empty space around the target object. In this paper, we are interested in finding the minimum number of push actions that lead to a scene where the target object can be grasped and retrieved. The general idea or motivation is that the robot can imagine the effect of an action, so plan a few steps ahead, resulting much smaller number of actions required. We propose to employ visual foresight trees to solve the problem. A deep interactive prediction network is used to predict future images. The Monte Carlo tree utilizes the predictions to obtain the shortest sequence of pushing actions that lead to an arrangement where the target can be grasped. Extensive experiments demonstrate that the proposed approach is highly effective for minimizing the number of actions in solving object retrieval tasks. A high-level description of the proposed solution pipeline is depicted here. Two deep networks are used for decision-making along with the Monte Carlo tree search. We will walk through the framework briefly and then describe three components in more detail. At the start of a planning iteration, an RGBD image of the scene is taken, and maskR CNN is used to classify the objects as unknown clutter or target object. With the target object located, a network called GraspNet predicts the probability of grasping the target. If the maximum estimated grasp success probability is larger than a threshold, the target object is considered as directly graspable, and the robot executes the corresponding optimal grasp action. Otherwise, like in this case, the target object in blue cannot be directly grasped due to the lack of free space for inserting a gripper around it. So, push actions must be performed to create space for grasping. We use the Monte Carlo tree search to find the best push action to take. Here, a second network called Deep Interaction Prediction Network predicts the motions of multiple objects and generates a synthetic image corresponding to the scene after the imagined push. Grasp network is used again to provide a reward value for each search node and detect whether the search terminates. A search node in the Visual Foresight Tree corresponds to an input scene or one imagined by the Deep Interaction Prediction Network. The corresponding action to the child node of root with the most promising state will be executed. The overall process is repeated until the target object is successfully grasped. We will introduce the three main components individually in the following few slides. The grasp network takes the image observation as input and outputs a pixel-wise table of predicted values. The red pixel means high, blue means low in terms of grasp success rate. Grasp network is trained while keeping the orientation of the end effector fixed relative to the support surface while randomly varying the poses of the objects. The input image is rotated before passing it to the grasp network. The rotation angle is evenly distributed around 360 degrees. As a result, for each input image, the grasp network generates 16 different grasp Q value tables. Then, grasps with the highest predicted values obtained from the trained network are ranked. The best choice without incurring collisions is selected for execution. The second network used in our method is the Deep Interaction Prediction Network. DIPN takes an RGBD image and a vector of the starting and endpoints of a push action. It outputs predicted translations and rotations for each past object, which are then used to create a synthetic image. Here, we sampled different push actions. The DIPN produces corresponding predictions. The DIPN in prior work is only evaluated in case of one step. We modified it to adapt for object retrieval from the clutter problem, which requires long-horizon visual foresight. Here, we are showing the multi-step predictions with DIPN. Given a sequence of actions, we start from time t. Prediction t plus 1 is produced by DIPN. Prediction t plus 1 is the input for producing prediction t plus 2, so on and so forth. The exact sequence of actions is performed by the robot. We recorded the intermediate images for testing the DIPN can be used for long-horizon visual foresight. In our study, with more objects, the DIPN is less accurate, but it still provides enough visual foresight for planning. With these two deep networks, now the Monte Carlo tree search is feasible to find the best solution. For example, the object in purple is the target that we would like to retrieve. In the first iteration, the target object is not directly graspable. Then a tree has been constructed by fusing Monte Carlo tree search and DIPN. This fusion generates an optimal multi-step push prediction as graded by grasp network. The best promising push action is then chosen and performed by the robot. We need the second iteration as a single push is not enough to free the target object. Again, a tree has been built to find the best action. In this tree, the best child node of the root has a child node that leads to the terminal state, where the target object can be directly grasped. Here the robot performs a long push that combines actions associated with these two nodes as one. After two push actions, the target object is now can be grasped. Here we show some demo videos on wood blocks. Two networks are trained in the simulation with similar bricks, as shown here. They work in the real world with negligible performance degradation. The target object is covered by purple masking tape. Our method works to unseen real objects. The target object is the 3D printed vehicle, which is covered by purple masking tape. We evaluated our method in 10 simple cases. Our proposed method Visual Foresight Tree uses an average of 2 actions, outperforms the compared methods. Furthermore, we evaluated our method in 22 hard cases between myopic method DIPN and VFT in both simulation and real experiment. We also compared our method to Go PNG, the prior work, which only tested their method in 4 cases in real experiment. We can still see the huge gap. For more results and code, please visit the link in our paper. Thank you for watching.